Okay, hi everybody. So this is my written answer to part A, which asks another map, gamma dot is nonlinear. So this is the symbol gamma. I think it's a Greek letter, and it's often used in physics and chemistry and other things. So you'll see it. So it's just the name of this map. And gamma prime, or gamma dot, is another map, and it says it's nonlinear. Compute it and explain why it's nonlinear. So here's my written answer. This would be full credit. Something like this. So gamma dot has formula t goes to this. Where did I get that? Well, I just took the derivative of t is 1. T squared becomes 2t. T to the third becomes 3t squared. So there we go. Compute it. Done. Now, explain why it's nonlinear. It is nonlinear since, for example, here's a linear combination just of one vector. C is a scalar, and t is a vector. Well, the input space is one-dimensional, so actually t is also a number, but we're thinking of it as a vector. Well, we can think of it either way. Regardless of how we think of it, this is the formula, and we see that we cannot pull the scalar out. This is one of the things that you can do for a linear map, and since we cannot do this symbol here means not equal. So because these two things are not equal, that proves that gamma dot is a nonlinear map. And so how do I see that they're not equal? Well, I compute this one. The left-hand side looks like this. I plug in CT for the t and t squared. Then, if I first plug in t, I just get the same thing again here. And then I multiply by c on the outside. You can see I don't get the same thing. For example, here's a c and here's a 1. The 2ct and the 2ct are the same, so that was sort of interesting. But here we see it's different. 3c t squared, 3c squared t squared. So that is my explanation of why this map is nonlinear. B, the derivative at a point is a linear map. So gamma dot, if we do it at a point, what we get is a linear map. So let's look at that. Well, it says compute it at the point t equals 1. Then explain why it's linear. Okay. Here is my written answer. Something like this would receive full credit. So gamma dot at the point 1, we read this like gamma dot at 1, or at, we called our input space by t, so at t equals 1. Or we could also write it like this, which will generalize much more nicely. It says that we have the derivative of gamma at the point 1. So we sort of read this in our heads as derivative of the map gamma at the input t equals 1. So those things map R to R3 again. So they have the same input space and same output space. And the formula sends, now I call this V because now I'm thinking of it as a vector. And then it sends it to d gamma 1 evaluated at V. So this is how we write it down. But in a formula, we see that this is V times 1, 2, 3. Or we could write the vector as a column vector, V times 1, 2, 3. So we're thinking of V as like a number because the input space is just a real line. So like 2 would go to 2, 4, 6, the vector. Because 2 times 1, 2, 3 is 2, 4, 6. So good, I computed it, right? It asked me to compute it at the point t equals 1. Well, here was the gamma dot, and I just plugged in t equals 1, and that's how I got this vector 1, 2, 3. Now the derivative sends an input to a multiple of that vector. Okay. And that you'll see that in the concepts videos, right? So watch those. Now I still need, so I computed it at the point. I still need to explain why it's linear. So here's my explanation. This is linear since the map, this map, sends a linear combination to a linear combination of the map applied to the vectors. So I had to do a little bit of calculating to get there, but you see that this piece and this piece are the definition of linearity. This is a little weird because, usually the C's are scalars, like each of the Ci's is a scalar, and these are vectors, but our input space is one-dimensional. But okay, it could still view it as a vector. A number is a vector because we can add it and we can multiply it by other numbers. And so this is okay. And you see what I did is I just plug in this into the formula. So I replace V by this linear combination of other V's, and it goes right there and it multiplies this vector. And so the way vectors work is you can just distribute and multiply each side by the vector separately. That's how vectors work. And then I noticed that here and here, I basically have this formula, except where V is replaced by V1, or V is replaced by, this V is replaced by V2. And so that's why I can write this. Okay, hopefully that made sense. Last part, part C. Compare the map V to the derivative of gamma at 1 of V with the map V to the derivative of gamma 1 at V plus gamma of 1. So both maps send R to R3 again. Let's look at them. Here's my answer. So I'm comparing these maps. One of them looks like this. Notice it goes from the origin and out. Now, the other looks like this. They're very similar. See, here and here look very similar, but the only thing is we're shifted. We don't start at the origin. We start at gamma of 1. So what's going on here? So here's my input space, R1. Here's my output space, R3. And so like E1, well, we're in one-dimensional space, so E1 is 1, 0. No, we only have one dimension. So it's just sort of 1. That's it. Okay? And 2E1 is, 2E1 is just 2. And so where do 1 and 2 get sent? 1 and 2 get sent to the vector 1, 2, 3. Why? Because remember, the formula was V times the vector. We computed it above, V times the vector. And so 1 goes to 1, 2, 3. When V is 1, we just get the vector 1, 2, 3. When V is 2, we get 2 times this vector. Well, that's 2, 4, 6. And so here they are. Here's the vector 1, 2, 3. Here's the vector 2, 4, 6. And that's what they look like. Now the other map sends V not to V times 1, 2, 3, but rather to the point 1, 1, 1 plus V times 1, 2, 3. And so we've shifted. Here is the shift. Shifted off the origin by gamma of 1. And gamma of 1 is 1, 1, 1, 1. So that's the shift. Now this sort of a formula will be important in linear approximation, which is the most important thing that a derivative does. So yeah, this is good. And this is my answer.